What's going on? I've been seeing a lot of really interesting deep learning evolution videos on YouTube. I've been wanting to take a stab at it for a while now. Machine learning is a new hot topic. I am unemployed. It's a Sunday at 2 p.m. and I'm still in bed. So I figured what better time to take a stab at it than right now. So here's my kind of first take. I've written a script in Python. It uses the PyMonk library, which is just the Python version of Chipmunk, which is a 2D physics simulator, as well as Pygame for the graphics. And I think the best way to understand this is to kind of just jump right in. I'm not going to do it in IDLE. I'm going to do it in terminal because it actually runs way, way, way faster, at least when you're printed to the terminal. So here we go. Here's what it looks like. I've gone through a lot of iterations of this. I'm going to kind of describe what's going on. It's a lot to take in right now, but I'll kind of work through it bit by bit. So right now, we have a random creature being generated inside this box that you see over here. A creature is defined as an interconnection of nodes, and these nodes can be either circles or these kind of random polygon shapes. If you're wondering what that sound you're hearing in the background is, that'll be my computer. It sounds like a jet. It's currently on fire. This thing crushes the CPU. And I also don't have a mic because I don't make videos, so you're going to have to deal with that. So these random creatures, they're nodes. The nodes can either be a circle or a polygon. The polygon can have random numbers of vertices. They have a defined weight, which can evolve, a defined friction, a defined elasticity, which means it affects how much it can bounce. And the interconnections are these damped springs, which have a rest length, a damping, obviously, and a stiffness, which can all evolve as well. The starting locations of the nodes can evolve, and there's a few other things that I'll get into. So what you're seeing right now is, up here you can see that there's 100 individuals in a generation, and I can change all that. In fact, I can do it right now. I made it so that you can do it with keyboard commands. Just makes things a lot easier, so you don't have to reset simulation and lose all your data every time you do it. So if I wanted this generation size to be, let's say, 50, so it runs a little faster, maybe get some results, we can do that. It doesn't actually take effect until the end of the generation for that particular thing. But moving on, you can kind of see we've got a certain amount of time in simulation. Right now it's set to 7 seconds, and you can adjust that as well with the commands. You've got a mutation rate, a Genghis bias, which I'll explain later, a death rate, and a fitness score, which right now we're at 0 because these creatures suck. Again, they're totally random. The first generation, these creatures are completely random. And let's speed it up so we can actually get somewhere. Hit S, goes twice as fast. Again, 4 times. 8, 16, I think 32 is the fastest you can go. Yeah, so most of my creatures are moving backwards right now, which is not ideal. What we're going to end up doing, though, is after this generation is over, you're going to kill a certain number of these creatures according to death rate. And right now we're at 0.5. So the bottom half of the creatures, right off the bat, murder them. They're gone. Let me get the terminal window out here so that you can kind of see what's going on. Here we go. Ignore the other windows. Let's close this, actually. Just look at this one. Right, so we finished our first generation. You can kind of see now that the generation size is down to 50. And we're on generation 2. Frames per second is a little bit affected, but no big. In fact, we can make this run super duper fast by just turning the graphics off entirely. It runs thousands of times faster. I hit G, graphics turn off, and this thing starts going crazy. It's off to the races. You can kind of see down here what's going on. With each generation, what it's printing out is this is the best in the generation. This is the 75th percentile, 50th percentile, 25th percentile, and this is the worst generation. -1 doesn't mean it went backwards a pixel. What that really means is that it cheated. And my way of dealing with cheaters is giving them a -1 score. Like the graphics engine, I mean, the physics engine is great, but occasionally it glitches out and will cross the entire screen. So I have to punish that somehow, otherwise it's just going to take over the next generation. So my way of dealing with that is when I detect cheating, give a score of -1, and it usually deals with it just fine. I'm going to turn the graphics back on for a second, just to show off my little histogram here, changing the speed back to normal. And you can see after 45 generations, we haven't really made it too far. The best one made it about 564 pixels, which is around here. Not great. They get a lot better, though. And I've come with some creative, really cool. My favorite creatures from the simulations that I've run in the past, I saved. I'm going to show them to you at the end of this video. They're really quite interesting. The histogram kind of shows you what's going on. Again, the green line is your best creature in each generation. 75th percentile, 50th percentile, 25th percentile. Red line at the bottom is the worst, and it's -1, so most of the time it's right below. But it looks like once we didn't have any cheaters in like the 4th generation, yeah. Okay, so more about the selection. The mutation rate affects, when a creature reproduces into the next generation, how much it changes from its parent. So here's a couple things that can change. You can add vertices. The vertices of each polygon node can move around to change its shape. The mass of a circle can change, the mass of a polygon can change, its thickness can change. That's that wall outline right there, which can actually affect the physics a little bit. You've got friction on all these things, elasticity, which affects bouncing. All that can mutate. And what mutation rate of 0.1 means is that within each generation, anything that can change, there's a 10% chance that will change. With a few exceptions, namely the chance of adding a node or subtracting a node or adding a connection or removing a connection is much less. I think it's 1/5 of the mutation rate. So that actually happens at a much lower rate, only because you don't really want that to happen as often. Right. So why don't we pause it for a while and let it run. In the meantime, while we're kind of developing something cool here, I'll show off some of my old ones. And now my computer's really freaking out. By the way, let's kind of look at, this is kind of interesting to look at. If you look at the activity monitor over here, Python uses 100% of one CPU, which for my computer comes out to about 12.5% of my total CPU. I believe, my computer says it's 4 cores, but every time I add a new process, every time I add a new simulator, it goes up under 12.5%, which leads me to believe it's actually 8 cores. I'm not sure what's going on there. You can see QuickTime, which is what's recording this video, is actually also using a huge amount of CPU, which contributes to why this computer sounds like a jet aircraft right now. Hopefully you can hear me over that. If not, I'm going to have to actually buy a microphone and re-record this. Genghis. Genghis is one of my own little spins that I put in this evolution simulator thing. I'm not sure if it's been done before. It probably has. But what I was doing at first was when you kill off half the new generation, so you're constructing a new generation out of the old generation, you kill half with the lowest fitness score, or however much percent according to death rate, and you populate the new generation just with copies of the ones that survived. So that would mean that if one of them was at the top of its pack by a lot, it would only get 1 child, and the one that barely made the cutoff would also get 1 child, and that didn't really seem right to me. And I call it the Genghis algorithm because what this new procedure allows it to do is if one of these creatures pulls a Genghis Khan, it can just impregnate half of the world. So that means that the number of children in the next generation is proportional to how high its fitness score was above its peers. The bias affects kind of how much it's weighted. So if I set the bias to 0, it does what I originally described, in that every parent will have the same number of children, or as close to the same number as 10, sometimes with a death rate of like 0.2, not everyone gets a child, and that's kind of decided randomly. With the bias set to 1, you have a much higher propensity for the most fit individual to have multiple children. And you can set that rate as high as you want. I had it set to like 50 before, and what that ended up doing is only the most fit individual would have the entire new generation. Every single other individual would not have any children, and the most fit individual would have all the children in that generation, which is good and bad. It can cause you to evolve faster, but you're also going to get stuck in a local maxima much, much harder, meaning that you're going to get stuck at one point, and you're not going to evolve any new features. It's not going to do anything crazy. Speaking of new features, let's see what we figured out over here. According to our histogram, it's been very slowly improving. Nothing too exciting. It's not doing anything too exciting. So 624 is where we're stuck at, which is around here. Hasn't done anything really fun yet. It's disappointing because I saw some really, really cool ones earlier that I'm going to show you right now before this video gets too long and my computer, explodes. And then I'll go back to the Genghis algorithm and really show you what's going on under the hood. So yeah, let's start with baseball. So right now the selection algorithm, how it's grading it, what its fitness score is based on, is its farthest rightmost node, its X location, is its score. So it doesn't matter what all the other nodes do. Only the farthest right node counts for its score. So what was happening before I fixed it is it would disconnect one node and just shoot it off like a baseball. And here's what it looked like. Yeah, see, it would kind of wind up. It would have the stiffnesses of a spring set really high, spawn the nodes in 2 very far apart locations, and as soon as it spawned, it would try to shoot one node to the other one, obviously make one very heavy, one very light, and then it would blast this other ball up the ramp. And that would get fitness scores in the tens of thousands, which is cool. That was because at the time in the simulator, when it was removing connections between nodes, it didn't actually check to see if it was orphaning a node. I've since fixed that, so you can't actually do that anymore. But that was kind of a cool midway result that it kind of figured that out. In fact, it figured that out in about 500 generations, which is kind of long. I find that it plateaus somewhere around 300 usually. You don't really get any breakthroughs after that. But every time I run the simulator, I get something new, so there's no telling. This has a long way to go, and kind of through these videos, you're going to see the evolution of my evolution simulator as it improves and what goes on. So let me show you another one. Unfold. It's kind of fun. This one, it's pretty cool. It kind of just unfolds itself. I did this in 22 generations, so it's not too refined yet. But again, it just sticks out that front node. It's got a little anchor going on back here. And then it just shoots the front node forward. And the score is only based on the front node, so that's actually a good strategy. Yeah, not too exciting now. Ratchet is fun. Totally independently of me teaching it anything, it figured out how to make a ratchet. Look how this works. It's got a small node and a ratcheting node on top of it. And when it gets to a certain level, it kind of clamps down and puts the brake on. So that was one of the cooler things about them. Again, only 150 generations in it figured out how to do that, which was sort of fun. Stretch for it is a very fun one too. There's a cartwheel right off the beginning, rolls forward, and then this is the really cool part. Look what this little arm does. Right before time runs out, it flings it forward just to get that last couple hundred points of score. And that one I figured out in 62 generations. How cool is that? That's kind of the results I was hoping to get out of this simulator, and it nailed it. So I'm pretty happy about that. This one's fun too. What it does is it rolls for a while, and with the damping of these springs, it times it perfectly when it gets to the top of its jump. It drops this ratchet, or this brake, into its wheels and stops itself moving forward right at the apex, which is very cool. Let's watch it again. There it is, right at the apex. I mean, and because it's selecting based on how far right it makes it, it times it perfectly. It does it almost every single time just right. Lowering the mutation rate will make sure that it doesn't screw up as much. Like this one screwed up, it didn't drop the hammer. But if you lower the mutation rate, you're never going to actually improve. Balance is really cool. This one ran for thousands of generations. And I'm just going to show it to you. Look what it does. Look at that. It's getting scores, I believe, up to like 2,000 with that. And it's 2 nodes with a very stiff spring. And it somehow just balances itself perfectly up this ramp. It's one of the cooler ones, I think, just how perfectly it worked out. Ramped card is fun. This is, again, back when it could disconnect a node. So it would disconnect a node. Let's watch it. It would disconnect a node and kind of use it as a ramp. It would land on top of it, and it would shoot this card up the ramp. Let's watch this one. See? That's pretty cool. And what it was doing earlier was this top one, again, would drop at the apex to lock it in place. Although once it evolved further and could make it farther up the ramp, the time would run out approximately where the apex was. This one mutated so the front wheel changed into a polygon, which is totally screwed with it. That's what Ramped Cart did. Motor glitch. All right, so now we're moving on to some of the later ones that I did. If I left them running overnight for thousands of generations, there's a weird glitch in Pinemonk that I can't nail it down. I can't select for it the way I did with some other glitches and give it a score of -1. Look what's happening. I have no idea why this happens. And if you know anything about 2D physics extension, maybe help me out. Look at that node. It just powers it up the ramp. Now I changed the resolution of the physics engine, the frames per second it runs, the iterations it goes through each frame, and it improved the problem only slightly. Look at this one, Cart 2. I got 4 of these. It started making these almost every time after a while. This one I ran overnight for 500 generations, with a generation size of 200. And that one screwed up, but look what it does after this. It's off to the races. Like, we're out of here. Just completely gone. See you tomorrow. Peace out. Goodbye, homie. Cart 3. You can kind of see, after running it all night, most of the improvement happens right at the beginning. After that, it's just a small crawl upwards. Again, it kind of plateaus a little bit after about 300 generations. Usually 300 generations. This one, after 700 generations, almost like it plateaued in the first 100. Because it got this strategy of just, rocket up the ramp with this glitch, this weird glitch. And that's kind of where it left off. So that one's pretty fast, and this is the last card that I recorded. This one's kind of fun. I have no idea what's causing that. And I've tried changing all sorts of parameters, stiffnesses, dampings, iterations, slop. No idea what's causing it. Can't fix it. Although hopefully it didn't happen. It looks like it didn't happen the one we're running right now because, we're not getting ridiculously high scores. This one's getting scores in the couple thousands. Right now we're at 700 with our peak. Oh, this is interesting. It must have plateaued because the one we're running right now, the top creature and the 75th percentile and the 50th percentile and the 25th percentile are not all that far apart. So it must be plateaued. Let's take a look at what it actually evolved while we were making this video. Looks like nothing. It's doing a weird unfolding thing. It's kind of cool to see what it came up with. No crazy breakthroughs like some of those other videos I showed you. What is fun to notice, though, is that it got this right off the bat, and it's kind of pulling all the percentiles with it. So half of these creatures are doing almost as well as the top creature. So the evolution is not really happening as fast as I'd like. So let's do something fun here. I'm going to change the generation size to 200. I'm going to change the simulation time to 10 seconds. Runtime, I think 10 seconds would be 300. It's in frames. Yeah, 10 seconds. Let's change the death rate to 0.5, that's fine. Mutation rate, we're going to up the mutation rate. So basically we're going to bathe the Earth in radiation. And we're going to get some crazy mutations. And hopefully we'll break out of this rut, because we're kind of doing the same thing over and over again for, we're at 500 generations now. It's not going to cut it. We're not going anywhere with this one. So, mutation Let's do 0.25. So we're going to get some really freakishly mutated creatures for a while. I'm going to run this. I'm going to stop the video here. I'm going to run this, and I will start the video up again. We got an interesting result. All right, so we're back now. We kind of did evolve something pretty cool, but first I want to go through the histogram before I unpause this and show you some interesting things that I discovered. So you can kind of distinctly see where I changed mutation rate, which was right here. Right off the bat, earlier I was talking about how the top percentile, 75th and 50th percentile, were all closely tracking each other. As soon as you up the mutation rate, that immediately changes. So 25th percentile drops almost to the ground, 50th peels off the first. But this is kind of what we wanted. We broke this plateau, and the top percentile got this little spike. It figured out something new to do. And it kind of brought the 75th and 50th percentile up with it above where it plateaued at earlier. Draw whatever conclusions from that you wish. The bottom 25th percentile, you see here, it was before, occasionally the worst individual would not be a -1, and it would kind of be up here. Well, no. When you add a mutation rate, now the worst mutations are always necessarily going to drive it into the ground. So that didn't really work out for the bottom part of society. Now did it? Let's see what it actually looks like, what it actually evolved. I think this is kind of cool what it did. You kind of see this a lot with these creatures. They can only do so much. They don't have muscles and neurons. That's for another project. It drops in anger, and then it slowly unfolds and shoves a node forward. Let's watch a couple of them. I'm going to speed it up so we can see a couple of them. So you can kind of sort of see what's going on. A lot of them screw up. Again, mutation rate is really high. But they're shoving that node out about as far as they can. What I'm going to do now is drop the mutation rate back down to 0.1, up the Genghis bias, and hopefully they'll converge again, and we can kind of see what the top creatures look like. And we'll do that now. And I'll pause the video after a couple of generations and show you what it outputs. That should do it. So graphics off again. Alright, so we're back. I accidentally forgot about this and left it running while I went to go make dinner and eat dinner. And yeah, it went through about 4,200 generations. I also cut my finger, so I'm having a hard time typing out right now. Don't ever cook with a machete-looking butcher knife. But interesting to note, you can see right here, right back here, is where we changed the mutation rate to very high, and again straight up high too. Then you can see over here is when I switched it back, because you can see the 50th percentile drops, and then it climbs back up starting here, and it matches up with the highest percentile as well. And I mean, changes have been slow, but it did get better. This is kind of what it came up with, and it definitely plateaued by now. It's settled in. It's not doing anything better. In fact, this is kind of a glitch because this spring is stretching a lot further than it should be. That's one of the glitches that this program has that I can't really put my finger on. So what I do is I select against it and give it a score of -1, but I guess it's still cropping up. It's not good. The maximum spring length is supposed to be the length of the bottom of this box, and that's not what we're seeing here, so something's wrong. I'll have to look into that. There's a few other bugs that I'd like to fix. That's the next step with this program. Really, the next step I have to take is adding a neural network and muscles so that we can evolve a neural network to control things and hopefully make them walk. I'd also like to try to select for maybe jumping height, something fun like that, and that's really the next step I'm going to take with this. I'm going to go ahead and end this here because this video is already way longer than I expected it to be. I realize I never went into depth about how the Genghis selector works, so I'll probably make a video about that if there's any interest. Also, if anybody's a whiz at PyMonk or Chipmunk, I might be able to explain some of the bugs that have been going on. Maybe reach out to me and I'll send you my code. Definitely not going to post my code publicly because it's definitely unreadable to anybody except for me. I'm an electrical engineer, not a computer scientist. This is one of the only times I've used a high-level language like Python. I'm usually working in C or something. So that's it for now. Stay tuned for more videos as my deep learning simulator evolves. I'll definitely post more interesting stuff, and thanks for watching.